In this lecture, what we'll be talking about is intensity data. So how do we go from diffraction spots to get intensity for HKO values? And then from there, how do we determine the electron density inside the unit cell? And how do we use the intensities of the HK or the HKO values to identify what type of symmetry is present in the crystal? And so that eventually leads us to identifying the space group or possible space groups for a crystal structure. So we'll get started with that. So today we'll be looking at intensity of diffraction data. And so just to kind of recap on our path to crystal structure determination, we've talked about X-ray generation, X-ray detection, X-ray diffraction. We'll talk about crystal growth sometime this week. We've talked about geometry, reciprocal lattices, and today we're going to talk about two things: intensity data and scattering factors. Now for data processing, you've been exposed to a little bit of this when we were doing the auto indexing the other day. Crystal Clear is an older software, but now we use Crystalus Pro. And so with the software, we're going to integrate intensities. So we're going to find HKL values and apply intensity to those HKL values, absorption corrections, etc. So all of this is done using software. Symmetry determination. So what this stage is you determine the HKL values that are absent and present, and from that you can determine the centering and different types of symmetry that are present in your crystal structure. And then at the end of the week, hopefully we'll get to structure determination. So we'll go through determining the crystal structure once we have the intensity data, and then interpreting and refining that structure. So today we're mainly going to focus on intensity data and scattering factors. Now there's a lot of complex math equations in this lecture, but we're just going to explain the equation. You're not required to do any calculation with the equation because it involves triple integrals, Fourier transformation, etc. So don't be alarmed if you see these very big math equations. The computer does that for us nowadays. So as we talked about, what we know depends on where the diffraction spots are on the image, because once we know the diffraction spots, we know where the crystal was, and we can calculate things like HKL planes that are responsible for the different diffraction spots, which deal with Bragg's law, which is constructive interference n over lambda. Once we find out which ones were constructive interference, we talked about yesterday, we can locate the diffraction spots in reciprocal lattice, and then once we know the reciprocal lattice, we can find the real space lattice, which gives us our unit cell parameters. So the diffraction pattern of the crystal is important because from that we can get information about the crystal to help us in our structure determination. What we still don't know, though, up to now, is how do we know whether a crystal is going to be primitive or centered crystal? So for example, is it going to be primitive or C-centered? And how do we know which one of the space groups that this crystal structure is going to fall in? So these are some questions we still don't know because there's 230 space groups. How do we know? How can we narrow that down from the diffraction pattern? And then lastly, how do we know where the location of the atoms are? So all we know up to this point is we know the unit cell lattice parameters, and from there we can infer something about the crystal system. And so to identify these three key pieces of information, we have to look at the intensities of the diffracted reflections. And so these are referred to as structure factors. So this applies some type of intensity to the HKL reflections, and from that we'll be able to determine if the crystal is going to be primitive or centered. What we can narrow down the space groups that the crystal will fall in, and we can also use the structure factors to help in finding the location of atoms in the crystal. So there has to be a method of calculating the intensities of reflection based on where the atoms are in the crystal lattice. And this is what we're going to be talking about today. And so where does the intensity we measure come from? The observed diffraction pattern, as we talked about, is a Fourier transform of the object scattering the X-rays, aka the lattice. So you have in the lattice atoms, the atoms scatter the X-rays. We get a diffraction pattern through Fourier transform. So that's how they're linked one to the other. And so the observed diffraction pattern is the sum of all the constructive interference of the scattered X-rays, aka the ones that obey Bragg's law. And as we know from crystals, atoms are arranged periodically throughout the crystal. So you have the same repeat unit throughout the entire crystal. Next, we know that X-rays interact with the electron density of the atoms. So if you have heavier atoms, they have more electrons, it's going to interact differently than, say for example, if you're comparing a carbon and a copper, X-rays would interact differently between the two because copper has more electrons than carbon. So it's going to be what we refer to just diffract more strongly with copper versus carbon because it has more electrons to interact with. And so since atoms are arranged periodically throughout the crystal, the electron density is also arranged periodically throughout the crystal because it's the electron density that interacts with the X-rays. They're found in atoms, so since atoms are periodically throughout the crystal, electron density is also periodically found throughout the crystal. And so we have to ask, is there a function that we can use to model the electron density in a three-dimensional crystal? So if we can do that, then we can find where atoms are from the electron density. And so what we can do is we can do Fourier transfer on the electron density to relate it to the intensity of the observed reflections to atom types. So if we know the intensity of the observed reflections, we can do Fourier transfer on that to determine the electron density in relation to the atom types. So once we know the electron density, we can determine the atom types that are found in the crystal structure. So again, it's a Fourier transformation between the HKL intensities. So whenever we talk about observed reflections, we're talking about HKL intensities, and we do a Fourier transform to get the electron density. So once we know the electron density, we can determine the atom types. So again, Fourier transform is just a summation of all the waves. And this is the equation we can use to determine the electron density. So we have, and we'll talk more about these symbols in a second, but rho is the Greek symbol for density. So the density at point XYZ is found by this long equation here. You'll notice that the HKL values are shown here. This phi is a phase issue or phase problem we'll talk about in a little bit. And F is a what we refer to as a structure factor, and it's determined from the intensity of the HKL reflection. And so what you do is you sum over all the HKL indices for that particular point to determine the electron density at that XYZ point. So again, rho is the density, electron density. F is what we refer to as the structure factor, the intensity of the reflection. H, K, and L are the indices, so the actual reflection indices, and this minus phi is what we're going to talk about in a little bit. Just mention it's a phase variable. So this is the equation we use to calculate the electron density. So as I said, rho is the electron density at any point in the unit cell. Its units are electrons per an angstrom cube. This is actually a real number, and when we start solving crystal structures, in the very old days when you would first open a initial point for a crystal structure, it would show you just regions of electron density in the crystal lattice. So you had to go in and identify what types of atoms were found at those regions of electron density. So the electron density at any given point is a function of the diffraction recorded, which is the structure factor F of HKL at all the reciprocal lattice points. So if we know the electron density, we know the HKL indices, we can calculate the structure factor. And this is where we'll get in a little while what we call the calculated structure factor, because now that you've assigned electron density to it, you can actually use the indices to find the structure factor. So you can go between structure factor, electron density, or electron density to structure factor. And so structure factor is a Fourier transform of the electron density back to intensity of the reflection. And so this is a very important component here, the structure factor. We'll be looking at that quite a bit. This is the key thing to solving and refining a crystal structure, is how well the observed structure factor matches the calculated structure factor. And so there's a structure factor observed for every reflection in the diffraction pattern. And again, it depends on the diffraction angles to determine what particular HKL indices it is. So the last two bullets are important, that all atoms in a crystal structure contribute to every structure factor to some degree, and we'll talk about that in just a moment. And the structure factor is equal to the observed scattering in reference to electrons for all the atoms in one unit cell at a lattice point HKL. So all atoms contribute to every structure factor. The structure factor is equal to the observed scattering of all atoms in one unit cell. But as we'll find out, each atom, all atoms don't scatter the same. Some atoms scatter more than others. Some atoms scatter less than others. So not all atoms are created equal. Different ones scatter electrons differently. So we have our reciprocal space diffraction reflections. We use that to determine the HKL indices. Then we get intensities for that, which are called the structure factors. Once we have the structure factors, the FHKLs, we can use that to determine electron density in the actual unit cell. And from that, we can determine atom positions. And so structure factors does include a complex and imaginary component. And as we'll see when we look at the real and imaginary components, it introduces a individual atomic component called the atomic scattering factor. And so when we look at the structure factor, it's the summation of not just the electron density, but also the scattering factors and positions of all atoms in that lattice point. So here we have structure factors equals an A HKL plus an imaginary component B HKL. And you'll notice here that you now are seeing this factor called F, which is due to the scattering, you could say, power of an atom. So every atom has different scattering ability. And so you sum up all the atoms to determine the A and B components, which gives you the structure factor. So now this atomic scattering factor is important because it depends on the type of atom you're using, the direction of the scattering of X-rays, and also the wavelength of X-rays you're using, because that will affect the scattering potential of the atoms. And this provides a way of telling you how efficiently atoms will scatter electrons compared to a single electron. So the F is a value in electrons. So for example, on this graph, we see we have chlorine, oxygen, and carbon. And you'll notice that chlorine F value is a lot greater than oxygen and carbon because chlorine has more electrons than oxygen and carbon. And so at the bottom, we see the sine theta over lambda. So the way you can look at this is the further you go out on sine theta over lambda, you're getting to higher 2 theta data. Because remember we talked about yesterday, higher 2 theta data gives us better resolution. And so you want your atoms to scatter efficiently at higher 2 theta. And so we'll notice here, for example, at 0.3 sine theta over lambda, chlorine, oxygen, and carbon scatter quite efficiently at 0.3 of sine theta over lambda. And remember, if you use a shorter wavelength, like molybdenum versus copper, it's going to change this value. Now, if we go to somewhere like 0.6, so the further out we are, chlorine still scatters somewhat effectively, but you'll see carbon and oxygen, their scattering power has diminished quite substantially because these are weakly scattering elements because they have very few electrons. And so the heavier the elements you have, the easier you could say it is to obtain higher resolution diffraction data because they continue to diffract strongly at higher 2 theta values. Whereas lighter atoms don't diffract as efficiently at higher 2 theta values because they have fewer electrons. And so you can relate the atomic scattering factor to the atomic number of the element. So the higher the atomic number, the greater the scattering factor. And this is where it shows up in the structure factor for each single atom. So you would include the scattering factor when you're trying to determine the intensity of the reflection due to each atom at that lattice point. So as we said earlier, the intensity of the diffracted X-rays drops off with diffraction angle because as you go to higher diffraction angle, higher 2 theta, the scattering ability of the species decreases. So at 2 theta equals 0, we consider atoms a point source where the F is equal to the atomic number. So if you look here at 0, you see that the scattering factor F is related to its atomic number. So where is it? Like oxygen is 8, carbon is 6, hydrogen is 1. So that's where they get the initial or the scattering factor at 2 theta equals 0 is the atomic number. And after that, as you go to higher diffraction angle, you'll see that it decreases accordingly. So we have some partial destructive interference that occurs, and this results in HKL reflections at larger 2 theta angles have lower intensities. And we talked about this yesterday. So the further out you are on the diffraction image, the larger the 2 theta value, generally the lower the intensity of those X-ray reflections. And we talked about also on yesterday that we like to have diffraction spots out to the edges of the image because that's very high 2 theta values. And so as you can imagine, as we go to higher 2 theta values, the scattering ability of the elements decreases. So typically you're going to result in lower intensities. And that's what's shown on the graph here. As you go to higher 2 theta values, the scattering ability of the elements decreases accordingly. So if you have a crystal structure that contains a lot of heavy elements, say you have an iron oxygen complex, for example, iron is a very strongly diffracting atom. So even at higher 2 theta, you may get relatively more intense HKL reflections because iron is still scattering quite effectively at higher 2 theta. And so this leads to higher order HKL reflections, which refers to smaller D spacing, which generally have lower intensities. So if you look at your HKL indices and their intensities, the ones that are higher order reflections would be lower intensities than the corresponding lower order reflections. So a higher order reflection, let's say you have the 100 reflection, a higher order reflection could be the 400 reflection. So the 400 reflection would have a lower intensity than the 100 reflection. Because if you remember from the HKL homework involving the X-ray powder patterns, if you have a 100 reflection at say 30 degrees 2 theta, the 200 reflection would occur at around 60 degrees 2 theta. So if you have a higher order reflection like 400, it would occur at say around 120 degrees 2 theta. So the higher the order of reflection, typically the lower intensity. And so higher order reflections are like, if you're talking about 100, it could be the 400 or 300, etc. Also, thermal motion causes scattering to decrease more rapidly because the atoms vibrate, which affects the scattering ability of the atom. So typically to resolve this, we like to collect data at low temperature. And usually low temperature is about 100 Kelvin. So at 100 Kelvin, you minimize the thermal motion of the atoms, making it more effective at scattering the electrons. Oops. So just a little bit more on scattering ability. So what I've shown you here is where 90 degrees 2 theta copper with copper K alpha radiation and 90 degrees with moly K alpha radiation. And you see with copper, if we look at carbon and oxygen, they still have relatively strong scattering ability. Now copper and copper 2+ by far are a lot larger. scattering ability. And even hydrogen, you can still see it has just a little bit of scattering ability when using copper. Now when we go to molybdenum, the scattering ability of copper and copper 2 plus has decreased, compared to using copper radiation, and carbon and oxygen have less of a scattering ability, slightly less than it did with copper when using copper radiation. One thing to notice is with hydrogens, it's almost zero scattering ability when using molybdenum radiation. So since the elements don't scatter as effectively with molybdenum radiation compared to copper, molybdenum radiation usually requires longer scan time, so longer exposure to X-rays to help build up intensity of those weaker reflections at higher 2 theta values. So if you did a experiment with copper radiation and the same experiment with molybdenum radiation, generally the one with molybdenum radiation will take a lot longer than the one with copper, because with copper radiation your elements have stronger scattering ability. So since they scatter more effectively, you don't need as much exposure to radiation. Whereas with molybdenum, the scattering ability is decreased. It's going to take longer exposure time to generate that high angle data that you need for the diffraction experiment. So generally, copper, when you're using copper radiation, the experiment is a lot faster compared to molybdenum radiation. And in general, hydrogen atoms scatter very weakly. So even with copper radiation, it's hard to identify where hydrogen atoms are. So that's why you need precise intensity measurements. And so usually with copper, it does a better job at helping you identify hydrogen atoms compared to molybdenum. And as we'll see when we start solving structures, typically we put hydrogen atoms on idealized positions. So we know where the carbon, oxygen, or nitrogen is, and from that we use calculations to calculate where the hydrogen atom would be for an sp2 carbon, for example, or an sp3 carbon, or a hydroxyl group. And so that's generally how you identify where hydrogen atoms are, because they scatter very weakly. It's very hard to determine their position. Now, it doesn't mean you can't, it's just very hard. And in some cases, for hydroxyl hydrogens, you can identify their position based on electron density, because you can see the electron density resulting from that hydrogen atom. And so yesterday we talked about resolution. And so with resolution, we said that for molybdenum, the resolution was about 0.83 angstroms, which is 25.1 theta, which is about 50 degrees 2 theta. And so to get the required resolution for molybdenum, it's going to be about 0.6 sine theta over lambda. So where is that? And actually, these are sine theta over lambda. It's 0.6. That's about here. That's sine theta over lambda. Oh yeah. So to get resolution quality data, we need about 0.6 sine theta over lambda, which is right about here. So when you're looking at 50 degrees 2 theta for molybdenum radiation, it shows up right around here, and you'll see at 50 degrees 2 theta, there's strong scattering abilities for most non-hydrogen elements. So carbon and oxygen scatter effectively, and so does copper. And so when you're doing a experiment involving molybdenum radiation, you want your diffraction data to go out to at least 50 degrees 2 theta, because that's the cutoff for 0.83 resolution. So just to kind of summarize, electrons affect the scattering ability of elements. And so the scattering factor is related or related to the atomic number. The higher the atomic number, the higher the scattering ability. At 2 theta equals 0, the scattering factor equals the atomic number, and it decreases from there. Using copper radiation, you get stronger scattering ability versus molybdenum radiation, as shown in this graph here. So at 90 degrees with copper, K alpha radiation, copper, oxygen, and carbon diffract, they scatter quite efficiently, whereas with molybdenum, this starts to decrease compared to copper K alpha radiation. And typically if you want to know the actual hydrogen atom position, usually you would submit this to synchrotron facility, which has a very powerful X-ray source, and you can determine hydrogen atom positions. So where does this intensity come from that we measure? So we have scattering factors, which leads us to structure factors and electron density, which gives us the intensity. And then we have types of atoms plus location of atoms gives us intensity. So if we know the types of atoms, we know where they're located, we can find the intensity of the reflections. If we know the scattering factors, it can give us structure factors and electron density information, which we can also use to find the intensity. So the intensity is proportional to the square of the structure factor. And so this is the equation that they can use to determine the intensity, or the square of the structure factor. And so when we're looking for intensity, one thing that we lose some information on is called the phase of the structure factor, which is this phi angle. And so this is usually called in crystallography the phase problem. So when you look at intensity, you lose some information about the phase of the structure factor. And this is because diffracted X-rays are in phase, which means constructive interference. But this is due to the fact that their phases are shifted by an integer of the wavelength. And so we do lose some information about these phases when we look at intensity. So when we're looking at structure factors, intensity measures the amplitude, but not its phase, and this results in the classic phase problem in what we have in X-ray crystallography. So again, intensity is the amplitude, phase is the amount of constructive interference, or how much the X-rays are shifted, their phases are shifted. And so we use this equation to calculate electron density. So we have the intensity, we have the HKLs, and then we have the phase. So from this, we get the electron density of that XYZ position. So again, the structure factor is the intensity, F of HKL. Then we have the HKL indices, and then we have the phase component. So from all of this, we get the electron density of that particular region of space. And as we talked about, the structure factor is a complex number. We looked at that. And so we can find the phase by using this equation here. And so there are two things we need. We need the intensity and the phase. And that's the two components you see that are used in addition to the HKL indices to determine the electron density. So when we process the intensity data that we've collected, when we're collecting data, there are going to be small oscillations in the omega angle. If you remember, we talked about the 4 angles on the goniometer. Omega is when the whole goniometer arm moves. And so the reason they do this is to get a wider profile of the diffraction spots. So as you're collecting the data, there's actually tiny movements in the crystal so that we get a better width profile of the diffraction spots. And then once we process these reflection data, we can determine the intensity values for each reflection. So you got to first identify the HKL reflections, then assign intensity to them, and then from that, we can use Fourier transform to determine the electron density at that particular region of space. So when we talk about indexing, indexing is just assigning each reflection an HKL value. And then we're going to talk, you may hear the word integration. Integration is we take the width profile of the diffraction peak and integrate it to determine the intensity of each reflection. So after you collect a series of data, you have to go through indexing and integration. So indexing, you assign HKL values to each reflection. Then you integrate to determine the intensity of each reflection. And so every experiment requires these 2 steps. Then after that, we do some what's called merging and scaling. And so if you have HKL reflections that appear in multiple diffraction images, so let's say you have the 100 showing up in multiple images, you just combine it into one reflection, having one average intensity. And so if we have symmetry equivalent reflections, these are collected multiple times throughout the data set. And we have some factors that tell us how well these intensities of the symmetry related reflections agree with one another. And these are referred to as RSIM, RMerge, or RN. And we'll talk about those in just a second. This tells you how well the intensities of the symmetry related reflections agree with one another. And so the lower the RNs, the better they agree with one another. And so once you do all these 3 steps, you do indexing, you do integration, you're merging and scaling. And these are all done on the software. So you'll go through each step, indexing, integration, merge and scaling. Then you're going to generate what's called an HKL file, which contains the HKL indices and their intensity, which is the structure factor squared values. And it's this file that you need to use in order to solve and refine the crystal structure. Without this file, you can't solve a crystal structure. So again, we start with diffraction spots, reflections. We do indexing to assign an HKL value with the reflection. We do integration to assign intensity, aka structure factors for each HKL reflection. And then we do some merging and scaling. So this is with reflections that are the same from multiple images. We combine and things like that. Once we do all of that, we get this HKL file that we use for structure solution. And just to give you some equations of how they calculate this R value. So for RMerge and RSIM, it's the sum of the HKL indices. Use the difference between the intensity of the individual indice divided by the average of the symmetry related observations. And so from this, they get a value of RMerge or RSIM. The lower this value is, the better that they agree. The most important one that we use, and this is something that you'll notice when you're solving structures, and this is one that's very important, is the RInt. And if your RInt is high, it's going to be a little bit more difficult to solve your crystal structure than if the R int is low. And generally, you want an R int less than 0.1. If your R int is greater than 0.1, it's not like it's going to be impossible to solve the structure, but there may be something wrong with the data. It's going to be a little bit more difficult to solve your structure. So again, you're looking for an R int less than 0.1. Preferred is an R int less than 0.05. So if it's less than 0.05, that means the symmetry equivalent reflections are in better agreement with each other. And so this R int is used to calculate to see how the average in the difference between the individual symmetry reflections is compared to the overall average of those intensities. So it's the average of the difference divided by the average of the intensity. And the lower this number is, the better your symmetry equivalent intensities are. So preferred is to have an R int less than 0.5. And when you're doing the integration, the indexing, the merge, and scaling, this value will actually show up for you. So you'll know this value before you solve the structure. And so if your R int is high, you can try to do a few things with the scaling and merging to help lower it, or else you may have to just go and recollect a whole new data set. So again, when it's greater than 0.1, doesn't mean it's impossible to solve the structure, but it may be very hard to get it to a point where it's going to be a publishable structure. So again, Rn is what we look at to see how well these reflections are. And so the lower that R int, the better they are. So that's good news. So just to kind of show you with the processing, so with indexing, as we saw yesterday, we can find the unit cell. So this is kind of a process that we go through. So we use indexing. It goes through, determines all the reflection spots, indexes the spots, determines the unit cell, refines it, and then we go to integration, where we assign intensities to these HKL values. Once we do that, we do our merge and scaling. So identical HKL data is merged together, and the corresponding correct absorption corrections are applied. Again, this is all done before we start solving the crystal structure. And so as we said earlier, intensity is proportional to the structure square of the structure factor. Here, the intensity of the HKL is equal to, we have a few different variables here, and these are different things that can be adjusted when you're scaling and merging. So K is the overall scale factor. It's a series of constants. L is referred to as a Lorentzian correction. So this accounts for when the crystal is rotated in omega. It accounts for the differences as the diffraction peak moves. Okay. These are all things you can adjust to help get better data. P is the polarization correction. It accounts for beam attenuation at different scattering angles. And yep. So these are just different corrections that they use to help determine the intensity of the HKL indices. And so A is probably the most important one. It's the absorption correction. And there are many different ways to account for the absorption correction. And this follows Beer's law. So it has an absorption coefficient called mu and the path length. And for molybdenum radiation, you don't have to really, you can just do what's called the empirical method for absorption correction, because molybdenum doesn't have a very big absorption factor. But with copper radiation, copper is a stronger X-ray beam. It has more absorption. So you have to account for the absorption correction. And so typically what we use for copper, and I can show you this when we look at the software, is we do what's called phase indexing. And we have different methods that we can use to help account for this absorption correction, or this absorption. So you can use analytical, which indexes the phases, and I index the phases to help apply a better absorption correction. Empirical, which is usually the default, which uses what's called multiscan. Then there's geometrical absorption correction and Fourier. And so what you can do is when you're processing your data, you can try different ones of these to determine which one gives you the best, RN. So which one helps give you the best intensity for your reflections. Now, there's also a decay effect, and with modern day diffraction experiments, you don't see this effect quite often, but there is something that you can use to help account for the decay of the crystal over time. And typically, if you do low temperature experiments, it helps minimize the decay of the crystal. But this does occur, and if it does, you can apply some factors to help account for the decay effects. So after doing all of this, you generate this HKL file. And this is the most important thing that you need. So from this, now we can start solving the crystal structure. And so your program generates this HKL file. It contains the HKL indices. It contains its intensity, which is the first numerical column, and it contains its uncertainty. You have to have this in order to solve a structure. If you don't have this, you can't do anything. In addition to this file, you'll need to know the lattice parameters and the atomic types in your, proposed atomic types in your crystal. So you got to know which atom types are going to be found in your structure. Once you have all three of those information, you can start solving the crystal structure. And so now that we know the intensity, we know its uncertainty, we can calculate what's referred to as I over sigma. And so I over sigma tells you, the quality of your reflection data. And so we have words we like to use called observed data. And observed data is typically when I over the intensity is greater than 3 sigma. And then there's unobserved. And so there are different sets of reflections based on the observed, which is the intensity is greater than 3 sigma. And to know which reflections are most reliable, we have to look at I over sigma. And so I over sigma, we want it to be greater than, 10 or preferred 15. So if your I over sigma is not, at least greater than 10, you have very weakly diffraction, very weak intensity data. So you want, I guess, again, I over sigma needs to be above 10, greater than 10. If it's less than 10, it's not as easy, I guess you could say. And then observed data is when the intensity is greater than 3 sigma. So it kind of ranks these reflections to see which ones follow this rule here. The intensity is greater than 3 over sigma. Now, if you been dozing off, it's okay. This is some dry stuff, but pay attention to the next set, because we're going to be using this intensity data to determine the symmetry of our structure. And so once we know the symmetry of our structure, we can determine some space groups for that crystal structure. So this is important. We're going to be talking about what's referred to as systematic absences. So now we're going to talk about how do we determine the aspects of symmetry from intensity data. And so we can't know the positions of atoms unless we know the rules for their arrangement. So we got to know the crystal system. We got to know its centering conditions, whether it's primitive or face-centered, axial centered, etc. And then we got to know the space group, or at least some proposed space groups, not just 230 space groups. So in order to analyze the symmetry a crystal has, we have to analyze its intensity data. So we're going to look at which reflections have similar intensities and which reflections are absent. There's no intensities for these reflections. Now don't get alarmed. I'm just showing you how they go through and do this, but we'll show you on the computer. Nowadays it does it automatically. You just need a little bit of insight to help you through the process. And so you can actually make symmetry assumptions when doing the integration, merge, and scaling. Usually there's an option to determine space group. So it goes through and does it for you in Crystal Clear or Crystallis Pro. It can determine the systematic absences and then determine or gives you some options for space groups. You can also do this in ShellX as well if you want. And so you don't have to reprocess the data if you assume too much symmetry. However, if you want to use ShellX, it usually does a better statistical evaluation of intensity data used to make the determination. But that doesn't say that the Crystal Clear or Crystallis Pro doesn't do Crystallis Pro does a better job than Crystal Clear did, so it's pretty reliable as far as space groups. And so in the old days, there was this program called XPrep that would actually go through, look for systematic absences in ShellX and determine what is the most likely space group. Nowadays, it's all built into OLEX. So the thing I'm trying to tell you here is don't be alarmed. You don't have to go through and do this by hand. I'm just trying to show you the mechanics so you understand what's going on when you see this being done on the computer. So if a crystal system imposes symmetry on atoms, it has to also impose symmetry on the intensity data. So if 100 is crystallographically equivalent to 010, then the diffracted intensities for these lattice planes should be very similar. So the intensity for the HKL 100 should be equivalent or close to the intensity of the reflection plane 1010, because they're crystallographically equivalent. They're going to be, their intensities are also going to be relatively equivalent. And so we talked about RSim or RMerge. These values tell us how well these intensities agree with one another. So the lower the value of the RMerge or RSim, the better that these symmetry equivalent reflections agree with one another. Now that's ones with similar intensities. We're also looking for ones that are systematically absent intensities. And so these are symmetry elements with translational components. cause some reflections to be extinguished due to destructive interference in Bragg's law. So here again, we're looking at symmetry elements with translational components. So translational components means centering, screw axes, and glide planes. So some of those symmetry elements can make some reflections absent due to destructive interference in relation to Bragg's law, because those symmetry or those elements have translational components. So only those components with translational parts can cause this destructive interference. So this does not include mirror planes, two-fold rotations, or inversion centers. So only those with translational components. And then from that, we can determine a series of conditions based on the HKL values that can be identified where reflection should be observed or absent. So if we know the space group, let's say we have space group P21, we know which ones are going to be absent because it has a 2/1 screw axis. And with a 2/1 screw axis, there are certain reflections that become extinguished due to destructive interference. So if our reflection data shows that this particular set of reflections are absent for screw axis, this tells us that we have symmetry of a screw axis in the crystal. So it could be, if it's monoclinic, it could be P21. So what causes systematic absences? We're looking at first the C-centered lattice. So we have a first order diffraction, which is 2d times 100 times the 100 sine theta equals lambda, equals the path difference for successive planes. And so this is the D100, so it's the black line. Now since it's C-centered, we also have atoms along the red lines. But these red lines here, since it's translated a half, remember C-centered, we translate along the A and B axes 1/2. So when we translate 1/2, we get a reflection plane right here. Now again, the gray planes or the gray spheres on the gray lines are the in lambda in phase reflections. Remember, Bragg's law is in lambda equals 2d sine theta. So we have in lambda, these are in phase. Let me highlight those. So the ones in blue are in phase reflections. Now the ones in the red, since it's translated a half off, in this case, the A axis, these are lambda over 2. Actually, let me change the color. And lambda over 2, as we learned yesterday, is out of phase. So there's no reflection. So these become systematically absent. Because the in lambda are in phase, the lambda over 2 are out of phase because they don't adhere to Bragg's law. So therefore, they're systematically absent. So now if we look at a screw axis, so we have a 2/1 screw axis parallel to the B axis, so we have a rotation followed by a translation. So we rotate this, we translate it, we rotate, we translate. So we're generating symmetry equivalent positions. So for example, if we have the 0, 1, 0, this is the electron density associated with the solid atom, so that's position 1 here. Now when we do a screw axis, remember we're translating. So we're translating a half a unit over. And so when we translate a half a unit over, we get this wave pattern or electron density wave of the hollow atom, which is the symmetry equivalent atom. and know that these two line up in destructive interference. So the peak of one and the trough of the other line up so that they destructively interfere. That means that this 0, 1, 0 would be systematically absent for a 2-1 screw axis parallel to the B. Because the axis you translate along is going to generate, again, if we go back to the previous slide, it's going to generate that lambda over 2 reflection plane, which is going to be destructively interfering because it's out of phase. Since it's out of phase, it's not going to be observed. So that's what happens with the screw axis. Since we translate along the B axis, that 0, 1, 0 is going to have another plane at lambda over 2. So these are going to destructively interfere, so that 0, 1, 0 will not have any intensity associated with it. And so based on this absence of the 0, 1, 0, we know that this particular crystal would have a 2-1 screw axis in it. So this is just everything that we just talked about. So again, the hollow atoms have the lambda over 2 out of phase, which causes destructive interference. So the 0, 1, 0 was not present. So you wouldn't see no intensity for the 0, 1, 0 reflection plane. So we call it systematically absent. And so that's what we're doing, is we're seeing what operators are systematically absent from the reflection plane to help identify symmetry. So again, this is a 2-1 parallel to B. So what we would say is a 2-1 parallel to B, the O, K, oops. We'll get to that in a second. Let me just click that. We're going to talk about the general classes of HKLs as well. So here, if we look at another screw axis parallel to the B axis, and we look at the 0, 2, 0 reflection plane. So on the previous slide, we looked at an odd reflection plane. Now we're going to look at a even reflection plane, the 0, 2, 0. So it's still a screw axis parallel to B, but we're looking at the 0, 2, 0, not the 0, 1, 0. And so if we look at the two electron density waves, you know that the 0, 2, 0 lines up constructively. So the 0, 2, 0 doesn't involve destructive interference, it involves constructive interference. And so therefore, since they constructively interfere, you're going to see intensity for the 0, 2, 0 reflection plane. And since this is a 0, 2, 0, displacement about half the B axis length causes the individual electron densities waves to be in phase. And so this results in constructive interference for the 0, 2, 0 reflection. So we notice that the 2-1 parallel to B 0, 1, 0 was absent, but the 2-1 parallel to B 0, 2, 0 is present. So this is even, this is odd. And so what we can summarize is we can in general say that the 0, K0 reflection indices that are odd are absent. So anytime you have a screw axis parallel to B, the odd 0, K0 reflections are going to be absent, the even are going to be present. So if you notice that the odd 0, K0 are absent in a reflection file, and the even are present, that tells you you have a 2-1 screw axis. So again, we can't do this for a two-fold. We can only do it for a screw axis because two-folds don't have any translation. And so by knowing the systematic absences, we can also relate the effects with atomic positions with the resultant structure factor of these atoms. And so here is kind of using mathematics to show you that these are systematically absent. So this is the structure factor for the single atom, its contribution. So F is the scattering ability, then we have the HKL equals this. And so we can expand it out. If we have 2 atoms, this is what it would look like. And so let's consider we have a screw axis along B. So we have XYZ goes to negative X, Y plus a half, negative Z. And so what we're showing you here is the mathematical aspect that shows you that these are going to be systematically absent, whereas on the previous slides we showed you a kind of a graphical illustration. And so what happens here is that since X and Z become negative, the X components and the Z components cancel out. So we did a screw axis, X and Z become negative, there's no translation, Y is translated, so we can automatically remove the X and Z components from the 2 atoms. And so since we only need to consider the OKO reflections, because what happens is since X and Z are absent or they cancel each other out, we only have to look at the OKO reflections. Again, it's OKO because X and Z cancel, only Y is left. So since only Y is left, because Y has the translation, we got to investigate the OKO reflections. And so the structure factors for the OKO reflections equals this equation here. And so we can do some math, and what happens is we remove common factors, we get, some exponential times 1 plus negative 1 to the k times the scattering factor. Now just by looking at this, 1 plus negative 1 to the k, if k is odd, negative 1 raised to an odd power is what? It's negative 1. So then 1 plus negative 1 equals 0. 0 times an exponential is 0. So the odd OKO are absent because it cancels out this equation. Now if k is even, negative 1 squared, for example, negative 1 squared becomes 1. 1 plus 1 is 2, is not going to be systematically absent. And so that's why for a 2-1 screw axis parallel to B, the odd O0 K0 reflections are absent because it makes this term here 0, because -1 raised to an odd power is -1. So that's why these 0 K0 are absent. Now if we take that same thing and we make K even, -1 raised to an even power is 1. 1 plus 1 is not 0. So the even ones are going to be present. And this goes for any 2⁻⁴ parallel to any axis. So for example, if we look at a 2⁻⁴ parallel to A, so in this one, we translate along which axis? The A axis. So with a 2⁻⁴ parallel to A, we translate along the A axis. Just like in this 2⁻⁴ parallel to B, we translate it along the B axis. So now what that means is that the H 0, 0 odd would be absent. Because again, it would factor down to this 1 plus -1 to the K when K is, or in this case H, 1 plus -1 to the H. When H is odd, it's -1, it cancels out. When H is even, it wouldn't cancel out. So for a 2⁻⁴ parallel to A, since you translate along the A axis, what you're looking at is the H 0 odd reflections. Are they absent or not? If they're absent, that tells you that there's a 2⁻⁴ parallel to A. Likewise, if we had a 2⁻⁴ parallel to C, since it's parallel to C, we translate along the C axis. So since we translate along the C axis, we're only going to be looking at the 0, 0, L reflections. And if they're odd, we should look to see that the odd are absent. Or you could look at the even or present, either one. But odd is better because it's the absent one. It's easier to find if something is absent. And so for a screw axis, if it's parallel to A, you're looking at the H 0, are the odd ones absent? If so, then there's a screw axis present along the A axis. If it's 0 K0, we're looking for, that tells us that the screw axis is going to be a 2⁻⁴ parallel to B. We look at the odd reflections, are they absent? If yes, then it's a 2⁻⁴ parallel to B. And likewise, a 2⁻⁴ parallel to C, since it translates along the C axis, we're looking for the 0, 0, L odd reflections, are they absent? And this is what you're looking for. You're looking for systematic absences to help identify symmetry elements that exist in the crystal. And the same thing would go with glide planes as well. So again, if K is odd, we get 0, so that means that this is 0, so it's not present. If it's even, we get observed. So now if we look at the C centering, so we want to know why are which ones would be absent for C centering or A centering or B centering, etc. And so remember, for C centering, X and Y get translated. Z does not. So translation occurs in the X and Y direction, so we're going to be investigating the H and K indices. However, unlike the previous slide, and pay attention here, this is where it can get a little confusing, since no coordinates were negative, we must consider all HKL values, because you know Z doesn't change, so we can't just drop Z. And so now if the now we have to look at, since X and Y translate, we have to look at the H and K indices. If they add together to be even, then it's as observed. If they add together and it's odd, then it's going to be absent. But again, this can be a variety of different reflections. Let me give you some examples. So if we have the 3, 3, 1, 2, 3 plus 1 is 4. This would be present. Since it's even, it's going to be present. Now if we have the 1, 1, not 1, let's say the 1, 2, 0 reflection, 1 plus 2 equals 3. This is odd. It's going to be absent for C center. So what you got to do is you got to look at all the HKL indices and see the ones that have H plus K odd, are they absent or present? If the odd ones are present, you do not have C center. If the odd ones are absent, then you do have C centering. So you're looking at the ones that were translated. Now, just to give you an idea of A centering, so A centering, we have X, Y, Z. We get X, Y plus a half, Z plus a half. So here you notice that we translate along the Y and Z directions. However, X doesn't change sign. So our systematic absence rule is if we have, K plus L equals 2n plus 1, which is odd, it's absent because we translated along the Y and Z axes. If K plus L is 2n, even, these are present. So if you see both odd and even present, it cannot be acentering. Acentering means that the odd K plus L are absent. So for example, the 1, 2, 1 reflection plane would be absent for acentering. Whereas the, say, 2, 3, 1 would be present because it's even. And so that's acentering. So again, you only have to look at the axes where translation occurs. And then we'll just look at B centering. So in B centering, we have X, Y, Z. We get X plus a half, Y, Z plus a half. So now if you think about it, we translate along the X and Z directions. So what we're looking at is, we're looking at if H plus L is 2n plus 1 odd, it's absent. So for example, let's see. For example, the 2, 1, 1 reflection plane. So 2 plus 1 is 3. That's odd. Is going to be absent if there's B centering. If H plus L is even, it's present. This is if B centering is present in the crystal structure. So for example, the 2, 1, 2. So this is how you know if centering is present in your crystal, is you look at these different reflection planes. So if you look at the HKL plane and the K plus L odd or absent, that tells you you have A centering. If you look at the HKL planes and you notice that every H plus K odd or absent, that tells you you have C center. If you look at all the HKL values and the H plus L odd or absent, that tells you you must have B centering. So this is how they can determine whether your crystal structure is primitive, C centering, B centering, or A centering. So for example, for monoclinic can either be primitive or C centering. So for monoclinic, you would only observe, a primitive space group or a C center. So you would look at the H plus K indices and see if the odd are absent. If the odd are absent, this tells you that you have a monoclinic C-centered space group. So that narrows down the possibilities of your space group. So again, what we're looking for, you can either look at two things: the reflection conditions, which means they're observed. So in this case, that would be the even number. Or you can look at the extinction conditions, which are absent. And I prefer to look at the extinction conditions because it's easier to see if something is absent versus present. And so if you see an extinction condition where all reflections exhibit this extinction condition are absent, then you would say these reflections are systematically absent. Okay. So on that note, we'll stop here for today. Tomorrow we'll pick up with continuing on systematic absences. We'll look at, for example, F centering, body centering, and we also still have to include glide planes. So for example, if we narrow something down to a monoclinic C-centered space group, it could be one of a few So these are all the monoclinic C-centered space groups that there are. So now that you've determined it's monoclinic, it's C-centering, you've gone from 230 space groups to 5 space groups. And from this, you can narrow it down even further, because tomorrow we'll talk about glide planes. And if your glide plane is not systematically absent, well, then we went from 5, we could narrow it down to 3. Now, if the glide plane is present, we've narrowed it down to 2. So we went from possibly 230 down to 5, down to 2 or 3 at the end. So this is how systematic extinctions help. They can narrow down the possibilities of space groups. And so the next lecture, we'll be looking at body centering, F centering, and glide planes, and doing some examples of determining space groups based on systematic absences. So that'll end today's lecture. I'll take some questions if you have any in just a moment.